Hello. So is Arnaud here? Okay. I think according to the schedule, I have 12 minutes to do this talk. So
No. I took the time, so you.
Okay. Should I? Okay. Well, recognizing that I am standing between you and lunch, I will try to go as quickly as possible. Okay. So I'll be talking about time frequency measures. Okay. So, right, this will be a pretty basic introduction, but it'll try to go through the various, data representations that are available in EEGLAB. Before I do that, I just wanted to reiterate about this P41 and clarify a little bit. It's a grant that will allow us to connect with people doing primarily clinical work. We're especially looking for people who have active grants, particularly NIH grants. The idea is to give us a grant to help people with other grants improve, expand their scope. And again, there's this site, this survey. If you are kind of fit in this criteria, please fill that out. And then finally, there are some dinner sign-up sheets out at the registration table. 3 of those dinners will have this P41 emphasis. So we're looking for people interested in maximizing information from clinical work. That'll be with Scott Makoto. People interested in experiment design and large-scale statistics, large-scale data sets, Arnaud and Cyril. And then people interested in using mobile brain imaging, MOBI. I'll be leading that one. So if this is really for people who are seriously interested in a kind of deeper collaboration with us as part of the P41. There's also 3 other groups. There's the EEGLAB mailing list one. So for all of those who've ever participated or read Makoto's awesome answers, you can finally meet him in person. And then there will be a SIFT dinner and a BCI dinner with Tim and Christian. Okay. So, our signals of interest, obviously, in this workshop are MEG and EEG, primarily EEG, I guess, for most of us. And, we want to describe dynamic characteristics of brain activity and relationship between different areas of the brain. So traditionally, there are various approaches to doing that. We can ask or answer these questions in the time domain. We can look in the frequency domain or the time frequency domain. So I'll be focusing on the latter. We all know that EEG can be described in terms of different frequency bands of oscillatory activity to which are given different meanings. We can look at spectrum of like a given channel or component of EEG, and we see overall that there's different amounts of energy in different frequencies. This is a completely static view, though. It's telling us sort of, for a given period of time, what is the amount of different frequencies. And as Scott showed before, there's clearly lots of time-varying power in different frequencies in the EEG signal. So the spectrum itself is not, it's just a very gross description, but it doesn't capture time-varying aspects. So that's where we'll get into time-frequency transforms. So a bit of historical perspective. A lot of these techniques are based on Fourier analysis, which in its sort of simplest form just gives you a spectral profile of a signal. It's been sort of elaborated to give time-varying frequency information through 2 methods, short-time Fourier transform, or more recently, multi-resolution wavelet transforms. And I'll talk about both of those. So here's the plan. Talk briefly about frequency analysis, time frequency analysis, and coherence analysis. So frequency analysis, the simplest goal is what frequency are present in the signal and how much energy is present for each frequency. There are a couple of considerations that I will just go through very briefly, and actually not at all, or just very briefly, amplitude and phase and windowing. There's actually more information in the slides that you can download, kind of a couple of bonus slides that I took out of this one that go into more detail, but I'll at least touch on those. So, at base we have Fourier analysis. The insight of Fourier is that you can describe any arbitrary signal as a sum of sinusoids, okay? For example, this signal here could be decomposed into a series of sinusoids. of different frequency and different phase. But by adding them together, we can gradually and more accurately approximate any arbitrary signal. If we look just at the amplitude of these sinusoids, that's what we get when we look at a power spectrum. But the actual Fourier transform here is the continuous time. There's also a discrete time Fourier transform that is done, say, by the FFT command in MATLAB. The key is that the results, these coefficients that come out of the analysis, are complex values. So they actually give us an amplitude and a phase for every frequency that's been analyzed. That's often kind of buried in the fact that we look at power spectra mostly. So just keep that in mind. So to describe the frequency, why not just take our signal and do an FFT? It seems like a good idea. You'd get amazing frequency resolution. So the frequency resolution of FFT is 1 over the duration of the signal, okay? So if we had a 100-second signal, we could have 0.1 hertz resolution. But do we really need such resolution given the scale of EEG? No. There's also a big disadvantage of doing this, that the Fourier transform suffers from bias and variance. So typically in MATLAB, you'll find a solution is using one of various things, so like a Welch's method, which basically takes many short windows of the signal, does a Fourier transform of each short window, and then averages those together. So that solves some of those. And then, but what I really want to talk about is the lack of temporal resolution. So first solution would be a short-term Fourier transform. Here the idea, again, is to take short windows of signal, do a Fourier transform of each of those windows. So you're basically taking a snapshot in time and saying, okay, what's the power spectrum for that window? And then we can slide that window along the signal to visualize time-varying frequency content. And we'll get to this disadvantage in a little bit, but I'll explain that. So here, kind of graphically, here's what you see. Signal, this blue box is the sliding window. And so we can analyze that window at a variety of frequencies. What I won't really get into in great detail here is that we typically don't just take the signal in the window and analyze it. We'll typically multiply it by a tapering function, so we smooth off the edges of the window. And the main reasons for that have to do with basically avoiding spectral smearing, which is what you get with a rectangular window. And there's some slides, more detailed slides in the handouts on that topic. But just the basic concept is what I want to get across here, that we're doing a windowed sinusoid. And so we can analyze each window at a variety of frequencies. And again, the result for each frequency is a complex valued number. It can be represented as a phasor. You'll remember that complex values have a real and an imaginary part. Well, you can plot that on a 2D plot, but you can also express those as an amplitude times a phase, this formula here. So if you kind of conceptualize each coefficient of the analysis as being this little phasor diagram, the length of the arrow is the amplitude of that given frequency, and then the phase of that arrow, which direction it's pointing, represents the phase of the signal at that frequency. So if we do that over a series of sliding windows, represented here with time going along the x-axis, for each window we get a complex number for each frequency band that we analyze. Here 5 to 30 hertz. Okay. So you kind of think of this as basically it's a two-dimensional complex valued matrix. What we typically do in EEG, in event-related analyses, is to do this spectrogram for each window that we've taken from whatever our event of interest is. So we can imagine a stack of those spectrograms, okay? And to actually compute what we think of as the spectrogram, we'll just average across those. There are two ways to do that. The typical way is to actually average the magnitudes of those, okay? So throw out the phase information. And then you get a spectrogram like this. Okay. So just a little bit more on amplitude and phase. So the power spectra describes the amount of frequency present, but that is not a complete description. We also need to know the phase. So all these frequency domain techniques return an amplitude and phase at each time and frequency. And again, to find power, we compute the magnitude, which discards phase. I'm just reiterating this because it's an issue that I find some people beginning frequency analysis don't quite appreciate, that underlying the plots that we show in EEGLAB, there's actually this complex valued representation. I think in the spirit of EEGLAB, which is to like throw out as little information as possible, the philosophy, like doing an ERP, you're getting rid of lots of interesting brain processes. Well, just keep that in mind, that looking at a power spectrum, you're actually ignoring part of the information. There's just one other concept that relates to windowing, which is that of time frequency uncertainty. Okay, so in theory, if we wanted to look at a spectrogram, we want to know how much power there is at each moment of time at each frequency. Well, ideally we could have, very focal resolution in time and frequency. So we could say, differentiate the amount of power in 1 hertz versus 2 hertz, and at 100 milliseconds, 101 milliseconds. Well, in reality, you can't have arbitrarily precise resolution in both frequency and time at the same time. And this is often formulated in terms like the Heisenberg uncertainty principle, but it's in terms of basically the sort of focus that you can make on the time domain and the frequency domain. The product of those is limited. Okay, so what that means in practice is that this is kind of interacts with like window size that you pick for your analysis. Okay, so a longer window will get you finer frequency resolution, but because you're doing a longer window, you're going to get poorer time resolution. Okay, and vice versa. A narrow window will give you good time resolution with poor frequency resolution. So schematically, this is something shown here. These would be sort of schematic spectrograms. Short windows, you can get many more of them per given unit of time, but you have worse frequency resolution, and vice versa. Okay, and just to show that, this is a series of signals from 10, 25, 50, and 100 hertz that just each play for 4 seconds. Okay, so with a very short window of 25 milliseconds, you can actually resolve individual cycles of the 10 hertz stimulus. So that's fantastically fine temporal resolution, but frequency resolution is very very broad. So you can see here, it's very hard to localize what the frequency is at 100 hertz. But as you increase the window size, you can see progressively through 125, 375, and 1 second, you can see that the temporal resolution gets worse. The frequency resolution sharpens up. In this case, it's a little hard to see the worsening of temporal resolution. You might say, well, this looks fine. But if you were able to focus in on these transition points, you'd see that there's quite a bit of blurring of that transition. These are actually very long signals, so it doesn't show up as clearly. So one criticism of the short time Fourier transform is that you're essentially looking at a given window length and you're analyzing all the frequencies. Okay, so it means you're analyzing low frequencies with a window length of a second. If you're, say, looking at 5 hertz, that would be 5 cycles, but you're also analyzing 100 hertz with a window of 1 second. So you actually have 100 cycles. Okay, so something physically doesn't seem quite right there. So the idea that, well, 100 cycles of 100 hertz, that's a long time for that frequency, right? It's oscillated for a long time. So the sense that maybe there's a different time scale might be relevant for different frequencies. And the wavelet transform is kind of designed to follow that intuition. The idea being that, well, why don't we just vary the window size with frequency? So that we have longer windows for low frequencies and shorter windows for higher frequencies. The idea there being that, okay, there's a characteristic sort of scale of each frequency, and we're looking at that characteristic scale. So in the kind of extreme case, we can compare our analysis windows like this. On the left side of the screen is what we would see for a Fourier transform, a short time Fourier transform. This would be our window length and our tapered windowing function. But you can see that the window length is the same across all frequencies. So again, exemplifying, we have a few cycles of this low frequency, but many, many cycles of the high frequency. Well, the pure wavelet transform actually uses the exact same waveform, but so the exact same number of cycles for each frequency. So naturally, the waveform gets shorter and shorter as you go to higher frequencies. Okay, so it's a constant number of cycles, and so the window gets shorter at high frequencies. And so contrasting that, what you can see that an FFT versus a wavelet, the same stimulus. As you go, this is plotted with low frequencies up top and high frequencies at the bottom, but you can see clearly that the wavelet at the higher frequencies has much finer time resolution. You can see these individually striated bursts of energy at high frequency, whereas that's all blurred out in the FFT, the short time Fourier transform. Okay. So with these kind of preliminaries out of the way, EEGLAB typically uses wavelet transforms for all of its time frequency analyses. You can use parameters that would give you a traditional short time Fourier transform, but in general, as I'll explain in a second, it uses wavelet transforms so it varies the time window according to frequency. So there are a couple basic approaches to time frequency analysis in EEGLAB. So the first is the ERSP, event-related spectral perturbation, okay, which is simply the change in power in different frequency bands relative to a baseline. It's a really nice figure from one of Scott's papers that shows this three-dimensional space that involves spectral changes at different frequencies, but then also changes in intertrial coherence, which I'll get to. So ERSP looks at this level here, where we're just looking at pure power changes at different frequencies. If you want to try it out, so in EEGLAB, plot time frequency transforms, component time frequency. This is not a practicum, but there's actually a little more detail about values you would enter into the GUI in the handout. So here's an event-related spectrogram. So this is what we talked about before. Just shows the time-varying amount of power in different bands. Okay. What the ERSP does is simply it takes a baseline period, typically negative latencies, the times before the event of interest, and it quote-unquote subtracts that out from the whole spectrogram. So that gives us a spectral change. So it's saying, okay, there was these various amounts of power in the baseline. We subtract those out so that we get more or less an even baseline. And then here, this shows us changes. So it means that at 20 hertz, there's less power following the event. At 5 hertz, there's more power following the event. And that's computed typically, for example, here, just basically taking the spectrogram at each time and frequency divided by the baseline. The baseline is computed per frequency. And we say, subtract it out because we're typically looking at this in dB scale, so log 10 scale. So, as you know, a ratio is a subtraction in logarithmic space. So baseline is subtracted, and we see event-related changes in power. And that's reflected in the units. This is units of power, and the ERSP is in units typically of decibels. Okay, so again, it's log transform, so it's looking at changes in power. Okay, one little practical thing, in these time frequency transforms, I think this is the parameter that confuses the most beginners. There are two numbers that you specify for the wavelet cycles. And so the first number is the number of cycles in the wavelet, in sort of the basic wavelet. And the second number is the extent to which the time window is shortened with increasing frequency. So 3.0 would be an FFT, or a short time Fourier transform, where there's no shortening of the windows. That's what I showed you before. 3.1 would be the pure wavelet, saying that basically the windows are going to have the exact same number of cycles. So they'll shrink a lot as you go up. Typical default in EEGLAB is 3.5, so it's somewhat intermediate between these. So it says basically we're going to compromise we'll reduce the high frequency time resolution a bit to gain more frequency resolution at higher frequencies. Okay, so you can see that these reduce in length, but not as much as in the wavelet. Okay, so I mentioned, that's the ERSP. Then we also have this concept of coherence. And in that plot, there was the vertical axis was ITC, or intertrial coherence. Many of you are familiar with this, but I'll just go through in some detail. So the goal of coherence is really to just answer the question, how much do two signals resemble one another? It's a simple concept. It's really just the complex version of correlation. So how similar are the power and phase at each frequency? Okay. And a variant which you've probably come across is phase coherence, so-called phase locking, which only looks at how similar are the phases of the two signals, ignoring the power. Okay. So you can really think of regular coherence being a power-weighted version of phase coherence, where you care about the power of the two signals. So the basic formula for coherence is basically the spectrogram for any given frequency and time of signal 1 times the complex conjugate of the spectrogram of signal 2. And so kind of just conceptually speaking, we're just multiplying two complex numbers. And as you know, so if we have this representation of amplitude and phase, multiplying those numbers gives us something that has product of the amplitudes, but with respect to phase, it actually looks at the phase difference between the two. Okay. So we can think of each Fourier coefficient or wavelet coefficient as a phasor vector, okay, with a length and a phase. This would be for two signals, and then these could be the different time points. So really, what we're looking at is the amplitude-weighted phase difference between the two signals. And if we plot up all of those phase differences on this compass plot, we can see that they're all have different lengths and different angles. But if we look at the sum of those, we get this little green arrow there, and that's what coherence is, just the sum of those phase differences. And the difference between regular coherence and pure phase coherence is whether you've just normalized these vectors to 1 before doing the calculations. So we use coherence in two main ways in EEGLAB. So the first is intertrial coherence, which is now we're not actually looking at the relationship between two different signals in the brain or two different sources in the brain. We're looking at the relationship of responses of a single source over time. Okay, so intertrial means between trials, but where trials are, for example, in a stimulus-evoked response, you play a sound, and you look at a trial. So the question is, well, how consistent is the response, stimulus after stimulus? And Scott showed you something before with the P3 that showed, well, it's fairly similar, but there are differences. So we'll go into that in a little more detail. So the phase ITC. So it's basically looking at similar to the coherence, but we're basically taking the normalized frequency coefficients. So we're getting rid of the amplitude in phase, and we're adding those up across trials. So for example, if these were 3 trials, they have different amplitudes and different phases. We're just going to look at the phase, and we just add those up, so we get a resultant phase vector. Now, so clearly, if these phases are all aligned with each other, if we add them up, take their average, we'll get a large resultant. If they're all pointed in random directions and we add them up, we'll get 0. Okay, that's the intuition there. So here's an example for 3 trials. Let's look on the left here. So with these 3 single trials, in this case, they all show a burst of energy, but you can see that the phases of the red, green, and blue curves are not aligned. Okay. Contrast that with this case on the right, where you see the same increase in power, but the phases are aligned. Well, point 1 is that the ERP cares about phase alignment. Okay, so when the phases are not aligned, we don't get a large ERP. When the phases are aligned, we get a large ERP. The ERSP, however, is, like I said before, is kind of phase blind. This is sometimes called the induced response, the induced power, where we just care about the power of each of these. We don't care about the phase. So you can see those are actually identical between these two. And then finally, if we look at the intertrial coherence, it's low in this case because all of the phases are different, but it's higher in this case because the phases are quite similar. So moving back to this diagram, we see this vertical ITC axis here. So it gives us a way to think about how ERPs actually arise, and then therefore what does an ERP mean about what's going on in the brain. Okay, and so there are two kind of main ways you can get an ERP. First is that you just simply have an increase in intertrial coherence. And even with no change in power, you can get an ERP. And that's this vertical range here. Or you can have change both in intertrial coherence and power. And I'll show you some examples of that, but just keeping those in mind. So if you see an ERP, you can't actually tell from that which of these processes generated it. Was it phase resetting? Was it change in power? Or was it both? And what Scott and Arno have developed in EEGLAB are methods for actually teasing those two things apart based on something called the ERP image. Okay, so let's take an example. This would be multiple trials of a given process with an event. Okay. If we look across time, we can see that there are regions where the phases are not aligned, but then there are times when the phases are generally aligned across trials. Okay, so if we simulate a lot of trials, 5 minutes, thanks. Generate a lot of trials, we can represent those in what's called an ERP image. And Scott mentioned this, but it's very simply, each trial is now a row of this color matrix. The color indicates the amplitude of each trial. Okay, so you can think of this, each row is like a waveform, but we're just color coding the peaks with red and the troughs with blue. And typically in the ERP image, there's some smoothing across trials to make these bands of color stand out more. What we can clearly see here is that before the stimulus, the phases are completely random. After the stimulus, we see these stripes indicating that the phase has aligned across trials. It gives us a big ERP. But the actual amount of color hasn't changed. So if we were to look at an ERSP, we wouldn't see any power change. But if we look at this ITC value, intertrial coherence, we see a peak of intertrial coherence. Okay, so this is an ERP that is arising only from phase resetting or phase alignment across trials. Okay. In contrast, I think what people often think of as an ERP involves power change. So this is another example of an ERP image. Now it's been sorted according to the phase following the stimulus. So you see these diagonal bands. What you see before the stimulus is that the phase is basically random, this diagonal stripe. After the stimulus, the phase isn't quite completely vertically aligned, but it's more closer to vertical. So summing up across those trials, that intertrial coherence is what results in an ERP. We can also see that the colors are deeper and darker at this time than they were before. Okay, so again, we have a combination of things going on here. So the ERP is created by intertrial coherence, which increases, but there's also a measurable increase in power. Okay, so again, this is just multiple views of the same data. Okay, and I think that's one thing that EEGLAB is particularly rich in and focuses on. All these views of the same ERP. And you can see also that it gives you more information in that for the ERSP, there's actually this period of lower power, which really doesn't show up in the ERP at all. Okay, so putting it all together, the display in EEGLAB, when you do this time frequency, it will show an ERSP on top and then an ITC spectrogram on the bottom. Okay, this is kind of a slightly different new thing, but basically it's just the intertrial coherence at different frequency bands. Okay, So in interpreting these, we can take any event-related process and look, say, okay, well, how did power change following the event, and how did the intertrial coherence change? So this is a very powerful way of looking at it. So just briefly to finish up, we can also look at coherence between two different signals. So looking at the relationship between signals. And this is clearly a huge area in what we want to understand. We want to understand how different regions of the brain are working together, how they relate to each other. But the concept is exactly the same when it comes to coherence. We're just looking for phase and amplitude alignment between processes. And that's simply down here between component set component time frequency, component cross coherence. So example here of two simulated theta processes. At some time they're not aligned, but at other times, they are aligned in phase. Okay, so choosing the EEGLAB plotting option, we get two plots. The event-related coherence plot is the first one. Here frequency is low at top. And so what this shows is that at low frequencies, there's a big increase in event-related coherence between these two signals. Okay, so it means basically that the phase around 5 hertz is aligned following the stimulus. It also shows you the actual value of the phase. So the phase doesn't have to be identical for coherence to give you a strong result. All it means is the phase difference has to be consistent, if you think back to that earlier plot I showed. So we're not asking are the stimuli the same, we're just asking is the phase relationship between them stable. So this is kind of, coherence is just one way of looking at the relationship between signals. If you're interested in this topic, go to Tim Mullen's SIFT lectures, because that actually shows a lot more about methods that we can use to examine relationships between multiple sources in the brain. And so one way of looking at this is to basically, each of these balls is a different source, and so the links between them tell us something about the relationship between signals. Okay. And then finally, this is really just kind of the beginning. These are kind of, I wouldn't say antiquated methods, they're well worn, but an issue with coherence, there are a number of issues with coherence. It's not the greatest method. First of all, looking at coherence between channels rather than sources is a bad idea because we have so much mixing at the channel level. So a lot of coherence is spurious. It's just because of the volume conduction. The other thing with coherence, it doesn't tell us anything about directionality. It just shows that, okay, the phase of these two signals is aligned, but we don't know which signal is controlling the other. We have no idea. And then finally, coherence and actually other methods are terribly sensitive to a common input problem, that two signals might look related, and we might then assume that they're talking to each other. Well, if they just simply have the same common input, that relationship is spurious. There may be no connection between those two signals, just that they're reflecting the same common input. And so Tim will go into great length about these issues and how they've been solved by more modern techniques using autoregressive modeling. Granger causality is probably something you've heard of. That's one method. That's actually has just as many problems as coherence when it comes to common inputs. But it does give you directionality. But there are more advanced methods that Tim will talk about that try to solve both of these issues. And finally, also this has all been sort of looking at kind of frequency bands in isolation. Well, there are many cross-frequency methods now. And so one that we'll talk about on Sunday is phase amplitude coupling, where you look at the relationship between the phase of one frequency and the amplitude of another. So Ramon will be talking about a new plugin for that. So I'll finish up there. This was just a very brief overview of the sort of fundamental time frequency displays in EEGLAB. But just keep in mind that there are many other advanced ways of looking at it that you can look at, that you can go learn more about during the workshop. Are there any questions? Besides, when is lunch?
I have a quick question.
Yes.
Why is actually the use of power so common instead of just magnitude? So why do we square the magnitude? Because we usually bias towards kind of enhancement of the signals rather than suppression, right? Especially for baseline correction. Why is this so kind of common?
Okay, so that's a really good question. So I mean, power basically has typically been used to, it's just the analog of variance. So you're really asking why are we looking at variance rather than standard deviation? It's the same thing. Power is like, it's like the variance of a signal. The calculation of power is exactly the same. So you know, why? Generally because the squaring makes it sort of, you know, it just gives you a positive quantity. So it's the amount of signal, okay? So you're absolutely right. So if power is a squared quantity, it's positive, how can we look at reductions of power? And so just going back to this figure here, the way you do that is by taking a ratio, actually. So a ratio of powers. And so with a ratio of powers, you can look at increases and decreases. The problem with ratios is that an increase, you know, can be anything from 1 to infinity, but decreases are between 1 and 0. So that's not good. So that's typically why we use decibel scales, okay? Because if you take a log of a ratio, now increases are from 0 to infinity, and decreases are from 0 to negative infinity. So we've taken that asymmetry in power between increases and decreases and made it symmetrical. Okay.
May I say it, Jonathan?
Yeah.
I mean, I originally made that decision to make that call. It's also, you should always go back to the physiological, plausible physiological, that so that you're basically saying if something increases your theta rhythm there and decreases your alpha rhythm, are those additive influences? Are you adding theta rhythm and subtracting alpha rhythm? Somehow getting the anti-alpha rhythm and subtracting away from the alpha rhythm that's ongoing? And the answer, that's not very plausible in most cases. That's an example, but in most cases, for instance, you know, the influence of serotonin nodes and some people are essentially multiplicative. They multiply and divide the signal, so that that makes this the log scaling effective and physiologically, I believe, more meaningful in most cases than thinking of it as an additive process. So it's a multiplicative process, and then convert it to linear, adding and subtracting by going from one to the other.
Thanks for that. So that's basically saying why are we doing a ratio of powers rather than just subtracting off the baseline, like you're typically doing ERP. So hopefully that helps. You can play with the different options in the GUI. We can talk about that later too. Any other questions? Okay, I'm being told to wrap up. So thanks very much. You know, feel free to, you know, grab us at any time to ask questions that you might think of later.
So actually we have